Okay, so then let's hand over to Faraz. Faraz Usmani is our first speaker. I will stop the share. And Faraz, if you could please start sharing your screen. Yes, full screen, excellent. Then Faraz, the floor is yours. You have 20 minutes, and I will give you a warning after 15. Faraz from Mathematica will today present joint work on fracking, farmers, and rural electrification in India. The floor is yours.
Great. Thanks, Niclas, and thanks everybody for joining. My name is Faraz Usmani. I'm a research economist at Mathematica based in Washington, DC. Super excited to be here to talk to you about what drives the effectiveness of rural electrification. So a quick preview before we get started. In this paper, we combine two natural experiments. The first has to do with the rise of fracking, or the shale revolution in the US. As fracking increases in the US, it induces a parallel commodity boom in the cultivation of this relatively obscure agricultural product called guar across northwestern India, which causes an exogenous shock to rural economies. Nearly simultaneously, India starts rolling out its massive rural electrification scheme and is picking which villages to electrify on the basis of a strict population-based threshold. And so we combine these two natural experiments within a regression discontinuity design to ask how the causal effect of electrification on labor market outcomes varies with exogenous changes in economic context. What do we find? These 6 graphs essentially summarize our main results. When combined with a large-scale exogenous shock to economic activity, access to electricity leads to a large reduction in the share of agricultural workers in electrified villages and a corresponding increase in the share of non-agricultural workers. When those complementary economic conditions are lacking, however, access to electricity on average appears to have no discernible impact. And so with that, we'll just jump right into it. What is fracking? Well, as some of you might know, fracking is the process by which fracking fluid is injected deep into the surface of the earth, where it creates cracks or fractures in underground rocks, so that the oil and gas that's trapped within those rocks can flow out and ultimately be harvested. And so fracking fluid is a key component of this process. So what is fracking fluid? Some of you might know that it's almost entirely water, but of the proportion that is not water, the single most abundant substance is something called a gellant. A gellant makes fracking fluid thicker or more viscous. This increases efficiency in a variety of different ways. Now, while there is a ton of experimentation around the precise cocktail of chemicals that different fracking sites and developers and operators use, the single most widely used gellant is something called guar gum, which is extracted from a crop called guar. So what is guar? Guar is simply a drought-resistant bean that grows primarily in the northwestern parts of India. When I say primarily, I mean primarily. India is responsible for 80% of global guar production. And in particular, one state in the northwestern part of the country is responsible for 80% of India's production, which makes this state, Rajasthan, essentially the epicenter of global guar production. And so as the fracking boom takes off in the US, these two graphs essentially show the dramatic increase in natural gas and crude oil production in the US from fracked sources. As the fracking boom takes off in the US, it induces a parallel commodity boom in the production of guar in India. This graph shows that India's exports of guar gum, for example, practically more than triple practically overnight. Now, this large-scale economic shock is not lost on anybody. Here's just a series of newspaper articles from around the height of the fracking boom that begin to give you a sense of the kind of transformative shift that might be happening on the ground. In fact, my co-author likes to joke that this exogenous shock is so intense that it actually induces a newspaper to change its name to The Guardian. But that just kind of gives you a sense of the kinds of people I like working with. What makes this exogenous shock so interesting for our purposes, however, is that nearly simultaneously, India begins rolling out its massive rural electrification scheme. This scheme, the Rajiv Gandhi Gramin Vidyutikaran Yojana, is launched in 2005, and it aims to electrify nearly 500,000 villages across 27 of India's 29 states. Now, rollout of RIGVI, as it's called, proceeds in 2 steps. In step 1, state-level authorities first submit so-called detailed project reports that delineate all the districts within the state that will be selected for phase 1 of RIG-V implementation. Once those DPRs are approved, phase 1 rollout, that is actual electrification on a village by village basis, is determined by a strict population-based threshold. Only villages with at least one habitation with more than 300 people will be electrified. And I'll come back to what a habitation means in just 2 slides. So this is what the country looks like at the time. These light green districts that you see spread out throughout are districts selected for one reason or another by their state level authorities for selection into RIG-V phase 1, but which have nothing to do with the cultivation of guar. These light blue districts in the Northwest are guar producing districts, prominent guar producing districts that for one reason or another were not selected for implementation of RIG-V phase 1. And these dark blue districts in the Northwest of the country are both prominent guar producing districts as well as those selected for implementation of RIG-V phase 1, that is village level electrification. Now, selection into RIG-V is clearly endogenous. We don't know why certain districts are being selected and others not. And so to account for that endogeneity, we'll limit our analyses to only RIG-V phase 1 districts and take advantage of spatial variation in the cultivation of guar across the country. And so I mentioned habitations. What is a habitation? A habitation is simply a spatially distinct cluster of households within an administratively designated village. This is a satellite image of the village of Budanpura. It's in our sample. It's located in the state of Rajasthan. And in our data, it shows up as having 3 distinct habitations, and you can actually see those in the satellite image, 1, 2, and 3. But it's this habitation level population threshold that actually complicates identification for us as well. So to deal with some of those challenges, we're going to draw on the identification approach developed by Vernig and Prionas 2016 originally. Imagine that this outer square represents a district that's been selected for electrification as part of RIG-V phase 1. This district consists of 4 villages, A, B, C, and D. Villages B and C clearly meet RIG-V's selection criteria. Each of these villages contains at least one habitation that has at least 300 people. So these 2 villages are going to be electrified as part of RIG-V. Villages A and D do not. But if we're looking to identify the labor market impacts of electrification, then comparing village A to B is probably not the right approach. Not only is village B considerably more populous, it also contains more habitations, suggesting that it's geographically different as well. This comparison between villages C and D runs into the same challenge, as well as this, and so does this comparison between village B and D. But this comparison between villages A and C seems like it might work. Both of these villages have exactly one habitation, and the population of village A is just below the threshold, while that of village C is just above the threshold, suggesting that on average, these types of villages are broadly comparable. And so that's exactly what we do. We restrict our analytical sample to single habitation villages only, so that the habitation population is the village population. We then further restrict our sample to villages whose population is within a narrow 50% bandwidth around RIG-V's eligibility criterion. And then, as I mentioned, we restrict finally our sample to only villages located in RIG-V phase 1 districts to account for endogeneity of district selection. And this leaves us with a final sample of nearly 8,000 Indian villages across the country. With this sample in hand, we turn to our data. Our data come primarily from 2 consecutive rounds of the population census of India. We obtain information on the sectoral breakdown of the rural labor force by looking at agricultural and non-agricultural laborers. We find information on the share of agricultural laborers in a village by combining cultivators who farm their own land and agricultural laborers who farm someone else's land. And we obtain information on non-agricultural laborers by combining household industry workers who produce and sell goods and services within the confines of the village, as well as the somewhat vaguely termed other workers, which collects every other profession aside from the ones listed on the screen. We're also able to get information on the number of workers at the extensive margin by simply looking at the total number of workers in the village's population. With these data in hand, this is the empirical specification that we estimate. Electrified sub VD is a dummy variable that equals 1 if this village's population exceeds the Rigby criterion of 300, and so it's electrified. Gwar sub DS is a dummy variable that equals 1 if that village is located in one of India's prominent Gwar producing districts. Tilde P is simply a population running variable. So in the second and third rows, we simply interact each of these terms to be able to estimate slope coefficients for each of these different groups of villages above and below the threshold. Y sub VD pre represents a pre-electrification value of the outcome variable. This isn't necessary for identification, but it does improve the precision of our estimates. And then finally, gamma D is a district fixed effect that controls for all unobserved district level characteristics that might independently induce variation in the level of our outcome variable. And so our coefficient of interest is essentially beta 2, which represents the additional impact of electrification in a particular village located in a district experiencing this large-scale economic shock. The standard RD identifying assumption is inherent in this approach. Essentially, we're assuming that in the absence of electrification, any potential outcomes would have changed smoothly at that Rigby threshold. This would be unlikely if villages were able to manipulate, for example, their population levels either by misreporting or in actuality, and thereby influencing their eligibility for Rigby. This is unlikely to be the case. Rigby, which was launched in 2005, used the populations as indicated in the 2001 census to gauge eligibility. Nevertheless, we do check for discontinuous jumps in population at the Rigby threshold and find no evidence that that's the case. We also check for discontinuous pre-electrification jumps in a variety of other observable village level characteristics, and again, find that this change smoothly at Rigby's threshold. And so with that, let's turn to some results. This is the same set of 6 graphs that I showed to you in the beginning. When combined with a large-scale shock to rural economic activity, access to electricity leads to a dramatic decrease in the share of agricultural workers in a village's population and a corresponding increase in the share of non-agricultural workers. But when those complementary economic conditions are lacking, on average, access to electricity appears to have no discernible impact. This is the same set of results from those graphs in table form. The top row represents the impact of electricity in villages located outside of India's booming Gwar regions. On average, the magnitude of these coefficients is relatively small, and they're typically statistically indistinguishable from 0. In contrast, in villages located in those booming zones, access to electricity leads to a nearly 20% reduction in the share of agricultural workers and a 70% increase in the share of non-agricultural workers. Interestingly, this effect is especially prominent for women. The share of women non-agricultural workers, for example, more than doubles. Now, we conduct a variety of robustness checks and additional analyses to try and think about this effect in a variety of different ways, and I'm happy to talk about that more in questions. But a fundamentally more important question that still remains on the table then is, well, why might non-agricultural employment actually rise in this way, particularly when we're talking about an agricultural commodity boom? Well, the cultivation of Gwar, that bean, might be a rudimentary agricultural activity that can be carried out without access to electricity, but the process by which Gwar turns into that magic fracking powder, Gwar gum, is an electricity-intensive industrial process, entailing some of the steps that you see on the screen right now. In fact, here's a couple of photos that we managed to get from the website of a Gwar processing factory located in the western state of Gujarat, just to give you a sense of the kind of equipment a Gwar processing plant is using. And so to begin to think about how Gwar processing establishments and Gwar processing units might be responding to these same set of circumstances, we turn to data from 2 consecutive rounds of the economic census of India, which covers the universe of establishments in the country. In our sample, approximately 100 million distinct establishments. A problem we face immediately is that Gwar processing is not one of the industrial codes that the Indian government uses to characterize and categorize these establishments. So we start by simply searching manually for any establishment that has the word guar or some variant of gum processing in its name to begin to understand what the guar processing industry looks like. And we find that every single establishment that we're able to designate as a guar processing factory falls into one of these 5 industry codes. Together, we consider this as the guar processing industry. So we now have data on the district level shares and the size of establishments that are in guar and non-guar processing industries, guar and non-guar growing districts, electrified and unelectrified districts before and after electrification. And we're able to use this, and I apologize for that, to essentially set up a quadruple differences estimator. I'm not going to walk through the interpretation of each of these different coefficients, but I do want to give you a sense of the interpretation of our coefficient of interest. Beta 7 in this case represents the impact on establishments, guar processing factories located in electrified guar growing districts post-electrification. What do we find? We find first that the number of establishments in those regions, in that industry, increases, and this effect is largely isolated to relatively small establishments. So we see this influx at the extensive margin of large number of new establishments entering that particular industry exclusively in electrified regions. At the same time, along the intensive margin, we see that relatively larger guar processing industries are rapidly expanding the number of employees that they have. So essentially what we're finding is that the share of agricultural workers that we saw reducing at the village level are being transferred into guar processing factories that are also taking advantage of electrification at the local level, where complementary economic conditions are also in place. And so with that,
about 4 minutes left.
Sure, perfect timing. So with that, let me conclude. We find that access to electricity, when combined with complementary economic conditions on the ground, leads to a large reduction in the share of agricultural employment and a corresponding increase in the share of non-agricultural employment. This appears to be at least partly driven by a very closely related industrial expansion, which is also electricity motivated. When these complementary economic conditions are lacking, however, we find that access to electricity appears to have no discernible impact. So what does this mean? Well, context and local contextual factors matters immensely for the labor market impacts of electrification. And in particular, the extent to which these local contextual factors can be identified and can be identified clearly ex ante, they can potentially be used to guide spatial targeting of very resource-intensive large-scale infrastructure projects. In particular, it also demonstrates the need to rigorously study what drives heterogeneity in the impacts of large-scale infrastructure projects, since that essentially determines what particular areas of different countries might benefit, especially from large-scale investments made to increase access to electrification, as well as other infrastructure projects. And so with that, I'll stop, and thank you for your time, and I welcome your comments.
Thank you very much, Faraz. A very interesting presentation. So please, if you do have any questions, put them in the Q&A box. We will be able to see them, but the audience is not. And then we can collect them for our Q&A session at the very end. Our next speaker is Raul Bajo-Buenestado from the University of Navarra. And Raul will talk about mini-grids and if they promote energy access. Raul, can you start sharing your screen?
Sure. So let me just... Okay, so can you see that?
Excellent. Yes, you've got 20 minutes. I will give you a 5-minute warning unless you're also ahead of time.
Actually, sorry, let me stop sharing one. Here it is. Okay. All right, so this is a joint work with my PhD student Federico here at the University of Navarra. So here I'm going to present. So actually, this is an extremely preliminary piece of work. So any comments are extremely welcome. Okay, so probably I don't need to motivate that the lack of access to electricity is an extremely important problem these days, particularly in sub-Saharan Africa. And we know that achieving, universal access by 2030 is going to be super costly. So here, the International Energy Agency estimates like this is going to cost like $50 billion, almost $50 billion per year. So given this enormous burden that achieving universal access imposes to governments and to third parties, it's important to identify least cost solutions and also to evaluate the effectiveness of different options.
Sorry, Raul, is the slide moving? We're stuck on the overview.
Yeah, okay. Is that now working?
That's moving, I think. Yes.
Yeah, great, thank you. So as I said, so evaluating different options is extremely important. And the evaluation of different options for expanding electrification has usually focused on two extremes, like either on large scale centralized projects, that is on the expansion of the national grid, sorry, or alternatively in small scale decentralized options, like these kind of solar panels that are becoming increasingly popular. However, we know that there is many developing countries are experiencing massive investment in mini grids, which are these kind of standalone systems that aim at providing electricity to a small group of consumers using one small generator, which is, is a middle ground option in between the national grid and this kind of distributed generation options. We know that mini grids are booming, and here you have like some numbers, and essentially this is like a multi-billion-dollar business. And particularly this important business is in sub-Saharan Africa. However, even though there is a lot of money allocated to this business, there is no real evidence on whether mini grids promote electrification. And moreover, we don't know any cost-benefit analysis on this matter. So the question we want to ask in this paper is, do they work? Do mini grids work? Are they worth it? So we want to estimate the causal impact of mini grids in terms of electrification and other variables. And we want to extract insights that are relevant for like many countries in sub-Saharan Africa. The context that we exploit here is this groundbreaking policy reform implemented in Tanzania. This was back in 2008, and since then, the number of mini grids in the country essentially like doubled, becoming Tanzania like the regional leader in terms of mini grids. So we're going to use geolocalized data on all the mini grids in Tanzania up to 2017. And we're going to combine this with different kind of surveys, also with satellite nighttime data, and with additional like power infrastructure in this country. Okay, so as I said, we want to identify whether these mini grids actually improve electricity access, and also if there are other kind of wealth-related effects. To do so, we exploit the rollout of mini grids across Tanzania. And of course, the challenge here is that mini grids are not randomly allocated across districts, right? So that implies we cannot compare treated and non-treated districts. The treated means districts that receive a mini grid here. So what we do is we exploit spatial variation in proximity to a mini grid. And where I'm going to explain a bit how do we do so. Like preliminary results, we observe an increase in the probability of connection of households that are close to a mini grid by 7%. And also we observe that those households are more likely to, purchase other energy dependent assets. And interestingly, these results are similar using different kind of data sets. Also, we observe that, households that are relatively close to mini grids also start using electricity as the main lighting source, which is also important in terms of, indoor pollution implications, because otherwise, if households do not use electricity to light their homes, they typically use like kerosene, paraffin, or other type of pollutant devices. I'm going to skip the literature because in the interest of time, probably I don't have time to explain that. So a little bit of background here. A mini grid is, as I said before, a standalone system. It's usually not connected to the grid, although here I put off grid. They're usually off grid, but sometimes they are connected to the main grid. We observe like a few in our dataset that are connected to the main grid actually. And these are like small scale, mini grids use like small generators, like no larger than 15 megawatts of power. The idea is just to provide electricity to a few villages that are nearby. And the generators are usually like powered by diesel or by hydropower or solar, or they combine like different technologies. These are the hybrid ones. And as I said, the idea is to supply electricity to a small group of users, and we have some heterogeneity in terms of ownership of mini grids, management, tariff, payment methods. And as I explained in the introduction, mini grids are an intermediate option in between the national grid and these kind of off-grid systems, like a home base, I mean. Okay, so I'm repeating myself here. So there is a massive investment in mini grids in many developing countries, particularly in sub-Saharan Africa. Why are they so popular? Two main reasons: because there is a decline in the capital cost of these mini grids, which is actually rapidly declining these costs, and also because many countries in sub-Saharan Africa lack of a proper network, national network grid, which implies that rural populations do not have access to the national grid. Then in those places, mini grids are potentially at least cost options to electrify villages. In terms of, regarding the Tanzanian context, so mini grids were present in Tanzania since the colonial times, and usually they were built around like this kind of natural resource facilities or agricultural facilities. And in the 70s, there was a project to connect these like original mini grids, and this create the embryo of the current grid, national grid. However, this national grid in Tanzania is very limited. And in fact, we see that compared to other countries, electricity access in this country, I mean, other nearby countries, if you compare the percentage of people that is connected with access to electricity in Tanzania is very low relative to nearby countries. So here I document a bit like this, kind of differences in access rate in Tanzania and in other countries in East Sub-Saharan Africa. Okay, so then the Tanzania government implemented this Electrification Act in 2008, and the goal was to attract investment, particularly in mini grids. So they basically provide subsidies for generation for small suppliers. So actually small suppliers, because the maximum capacity of the generator they could install is like 10 megawatts. And this is kind of like a very interesting, like very modern, let's say, policy. And actually, as a result of this, the number of mini grids in this country incremented a lot. And as of 2016, there are like almost 110 mini grids across the country with a total capacity aggregated of 150, almost 160 megawatts. Right? So here you have the map of the different mini grids that are in this country. With the triangles, you see those installed after 2000, which is the first year for which we have household data. Also here, if you want to check, like in terms of different technologies, we see, the installation of mini grids in different kind of technologies. We see like increments in the hydropower mini grids, biomass, diesel, hybrid, and solar. So we have, again, heterogeneity here. So the empirical framework here, the challenge is that the location of mini-grids that were built is obviously not random. So we cannot compare districts that are, treated with those that are non-treated. So here we follow some literature and exploit the proximity to these mini-grids. And we exploit in particular two facts. So first we exploit this time effect. So we check what is going on before and after the mini-grid development, and also the location effect. So we compare households that are relatively close versus those that are relatively far. And for this, we need some assumptions here. So the first assumption is that at the very small level, like the regional, like almost like at the village level, the location is more or less exogenously given by some kind of like different geographical features. So I'm going to give an example in just one moment. The second assumption that we need here is that households that are close to mini-grids are more likely to benefit from it than those that are relatively far. So here I have one example. So suppose, not suppose actually. So this is like the mini hydro or the mini-grid hydropower in the middle of the country. And in order to install this mini-grid, you need to take into account the slope of the river, because in order to be like successful, you need steep slope. Therefore, the installation of mini-grid is here just because you have a greater slope for the river here than if you compare the slope of the river a bit upwards and downwards. And the second assumption means that, once you install this mini-grid here, this town is more likely to benefit than this town, and this town is obviously also more likely to benefit than this one that is far away, and for sure more likely to benefit than this one that is far away, or this one. Here you can see this as an illustration, what is going on. So this is the radiance of another mini-grid. This is biomass power before and after the installation, and consistent with this idea, we observe additional increase in radiance after the installation for those areas that are very close to the mini-grid. And here you have additional evidence. We see an increase, so this is the average nighttime radiance for different like rings. So this is like the first ring, like 1 kilometer close to the mini-grid. This is like between 1 and 2 kilometers, between 3 and 4, so on and so forth. And you see that here for the first one, up to 5 kilometers, we see a more radiance than if we compare with the other, areas that are within 5 and 10 kilometers away from the mini-grid. And we use this as a threshold to identify who are potentially the treated areas and the non-treated ones, in a close proximity to these mini-grids. Finally, we need this common thread assumption that in the absence of the mini-grid, locations that are close and far from the mini-grid will behave in a similar way. With all these assumptions in mind, here we exploit the kind of a standard diff-in-diff approach, in which we use like a dummy. If we observe cluster C with a mini-grid, cluster is defined in the DHS way, like in the survey data. And we interact this mini-grid. So mini-grid here is, if the cluster C is within 5 kilometers from a mini-grid, and we interact this dummy with another dummy, which is post, that takes the value equal to 1 if or after the installation of the mini-grid. We have some kind of control variables, region-specific time trends, and other fixed effects that you should expect in this kind of environment. In terms of data, here the mini-grid data was obtained from the World Resource Institute. So we have all of them geolocalized, and we also know the year of installation, except for 12 of them, which we drop. We also know the kind of technology and additional data. We have also data on transmission lines for this country, other plants, substations. Also, we have data on nighttime between 12 and 2016. And we combine all this data with two sets of surveys. The first set is from the DHS, We use data from 1999 to 2017, and also from the National Panel Survey of Tanzania, and this data goes from 2008 up to 2014, so it's more limited.
You have about 5 minutes.
Great. So outcome of interest, we're going to focus on whether households are connected to electricity and other wealth-related outcomes. And then I have a kind of usual controls, age, education, like gender, and rural dummy. So I'm going to jump to the results here. So first, this kind of preliminary evidence. So we will see that this is like the treated areas. The nighttime is increasing after the installation of mini grids. Nothing, we observed nothing in the years before. Additional data here. So at the beginning of before the installation of the mini grids, using both the DHS and the national panel, we see similar kind of percentage of people connected, but this changes a lot once the mini grid is installed. And here I have the main results with a zoom in for you. So we see that the mini grid dummy interacted with post is positive and significant when we check electrification rates. So we see that the installation of mini grid increases electrification rates by about, let's say, 7%, although this coefficient is a bit larger for the National Panel Survey dataset, probably because we have very few observations, I don't know. And also we check like pre-trends, and here we observe like no pre-trend, significant pre-trend in the most robust specification of the model, either both in the DHS and the National Panel Survey. And then we check also, like as I said, wealth-related outcomes. Here we check first using the DHS, what is going on with a wealth index that the DHS has. And we see that the installation of the mini grids has a positive effect on this wealth effect. And again, we see no pre-trends here. And also we check kind of other what is going on with other assets that require electricity, like whether they use electricity as the main lighting source, whether they have TV, refrigerator, cell phones. All of them have positive impact. I mean, the mini grids have positive impact on them. Here is the same, just zoom in for you. But here we see positive effect, refrigerator, cell phone. And here, if you wish, a placebo is what is going on with bike ownership. Bike ownership is presumably not affected by mini grids because bikes do not require electricity, and we see no effects. And this is basically what I have for you. If you have any questions, I'm more than happy to take after the next presentation.
Thank you very much, Raul. Very interesting work on mini grids here. Our next presentation will be by Dina Pomeranz from Zurich. Dina, do you want to start sharing the screen?
Alejandro is going to actually share the slides for me because I have a technical problem and I can only use Zoom on my phone. But hopefully this works. So you can hear me and you can see the slides, right?
Yes, we can hear you fine, see you fine, and the slides. I think, are the slides moving? Let's check. Not yet. Can we go one? Yes, okay, it's moving. Excellent. You've got 20 minutes and I'll give you a 5-minute warning.
Can I turn this? Does this work? That way it's bigger. Okay, oops. Sorry. Okay, technical challenges on the phone. Okay, so yes, I'm very excited to present this project, which is the first time that I'm presenting it. And I'm very much looking forward to your feedback because this is a bit outside of my typical area of research where it's more about public finances or firm development. And this is joined with Dina, who is also here in the session, and Isabel Günther, who are both at ETH. Yes, and it's about solar. So as you have said in the introduction, we went from macro to micro. So this is off-grid solar lines. You can go to the next slide. So yeah, so why I'm excited about this project is climate change and lack of access to energy are sort of two big challenges at the same time, and they may seem in tension, as we want to give everyone access to energy for all the reasons you have outlined in your papers that are all the benefits, but also many people are concerned about energy use by, growing low and middle income countries and what that's going to do to CO2 emissions. So in this session, people may probably familiar with this problem that over 750 million people still lack access to electricity in the home. And in sub-Saharan Africa, that's actually more than half of the population who doesn't have access. Most of the people without access to electricity live in rural areas and rely on fossil fuels, namely kerosene, for lighting and cooking. And this fossil fuels produces emissions that are obviously harmful for the climate, but also to human health. So it's estimated that 750 tons of black carbon are generated from the use of kerosene lights every year, equivalent to 4.5% of US CO2 emissions. So oftentimes, we may say, okay, the low-income countries have very low CO2 emissions compared to rich countries. We may not want to worry about that too much. But insofar that we do worry, actually, these kerosene use is a big share of what people do pollute. And in addition, household air pollution is responsible for millions of premature deaths, and kerosene in the house are a big part of that. So there are high hopes for off-grid solar to increase energy access because the prices of solar lanterns has come down so much. But as you know, many times engineering projections and development solutions are very exciting, and then in the end, the actual efficiency gains from novel technologies may not be as high. And so in this paper, we measure the effect of solar lights on household emissions through the reduction of kerosene consumption, as well as how price sensitive is take-up and effects on education and health. So this is one area where I'm interested in your input, because as far as we have found, prior RCTs on the effect of solar lights have mainly focused on education and health and not on the reduction of CO2 emissions. But if anyone's aware that we have missed something, I would certainly appreciate suggestions. So what is it that we do here? So it's a randomized field experiment among over 1,400 households in rural Kenya, where kerosene was the predominant energy source for lighting. That was implemented in 2015-16, was actually part of Dina's PhD thesis. And the treatment has, the intervention has 5 treatment arms and a control group. These are all a distribution of solar lights through schools. I'll tell you more about that on the next slide. And the main variation between the treatment arms was whether a light was offered and at what price. So one group was offered the light at market prices, but conveniently being able to buy it at the school and with information about why that might be a good idea to buy. And then some had a small subsidy that had to pay $7 instead of $9. The third group had a high subsidy where they had to pay only $4, and the fourth group had a full subsidy where the light was free. And then we have an additional treatment group where it was also free, but the light was larger and stronger. So in practice, this was implemented through schools, and students were randomly selected from grades 5 to 7 in 20 randomly selected schools out of the public school universe in Western Kenya. And between 40 and 80 students per school were sampled, depending on the school size. Then a baseline survey was implemented at the school, first with the randomly selected students, and then a few days later with the guardians who were invited to come to the school for the interview. And at the end of the survey, the guardians were offered one of those randomized treatments. So the control group didn't receive any light. The free solar lights groups received the light right there. And the other treatments received a voucher to purchase a light at the school 4 to 6 weeks afterwards. And then 7 months later, there was a follow-up survey at the school with the students and at home with the guardians. So to preview the results, we look at 3 dimensions. First, the effect of subsidies and the reduced transaction costs from being able to just purchase this at the school on the demand for solar lights. And we find that it responds strongly to the price. And then second, and I think this is the most central contribution of the paper, we look at the environmental benefits in terms of kerosene purchases and emission reduction. And we find that a 64% reduction in households' monthly emissions for lighting in CO2 equivalents. And this is an estimated reduction of 2.1. If this were scaled up for the whole country, this would have an estimated reduction of 2.1 megatons of CO2 equivalents per year. And then also we sort of replicate findings from other papers about the private benefits of solar lights. Actually, I'm not sure. The first part actually may also be a novel contribution, which is in terms of energy expenditure. So we find that is about a 50% reduction in household energy expenditures. And so even for purely that result of having lower energy expenditure, the lights would actually be net present value positive after 16 to around 24 months for the households, just for that reason alone. And then there are also, in addition, significant improvements in respiratory symptoms and eye health. We don't find any benefits for school performance. We do find that the students do more homework, at least that's the reported difference, but also they sleep less. So I don't know if this is because of that, but in the end, on net, we don't find any effects on test scores. Yes, it may also be the case that homework in this context is not super conducive to actually improving the test scores. I don't know enough about the Kenyan education system, but in any case, we do not find higher graduation rates or higher test scores or anything like that. So that's in a nutshell the summary of the paper. So we have lots of different data. We have baseline survey from the students and from the guardians, the follow-up survey from the students and the guardians, and then administrative test scores from both before and after the intervention, and then also after the intervention, the Kenya primary school graduation standardized national test, which is at the end of grade 8, and we can look at the results for that. Okay, so this is probably hard for you to read, but this is a sort of a balance table and baseline summary statistics. So you see that only about 1% of this population is connected to the grid, and only about 5% had a solar light before. And then it's just to show that it's balanced by grade, and it's balanced by which guardian showed up, and household size. Where it's not fully balanced for some reason, which can be expected from random noise that sometimes happens, that we have some significant coefficients for the gender, both for the student and for the guardian. So we'll have respondent fixed effects in all our analysis going forward. Okay, so then on take up, we find that it's very price sensitive. We also find, and this was a bit surprising to me, there is no discontinuity at 0. You might be familiar with other preventive healthcare interventions that it makes a huge difference for the households if it's 0 or some copay. And in this case, we might have expected this to be even stronger, because if it was free, they would just hand it to you. And for the copays, you actually have to go to school again to buy one. Nevertheless, we find that the slope is pretty linear across the 4 price points. We also don't find that usage is lower if the lamp is free. That's sometimes a concern when we distribute stuff for free, whether people would not use it. And we do not find that to be the case, which is important when we consider whether it would be worth scaling up the free intervention here at a national level. Seems like it doesn't affect usage, and take up would go up a lot. Okay, so we find that first of all, when households have access to the light, they have any type of light, 22 minutes more per day on average, up of, from 3 hours and 20 minutes in the control group. But just the students use it, not the adults. And there's also less probability of lighting interruption. And this is maybe why we find the homework increase afterwards. So we're pooling now. Oh, so I forgot to say, we're now going to pool all type of lights for the rest of the presentation, because as you have seen it, the price point doesn't actually affect the usage. So owning light reduces kerosene use substantially. This is really the key part of the paper. So the number of kerosene lamps used falls by almost half. There's a 30% lower probability of using any kerosene light on a given day. When people asked yesterday, did you use it? A 2/3 reduction in kerosene purchase and energy expenditure falls by almost half. So that's pretty large. And so what does this translate to in terms of environment? So here we're basing on the work by Lam and co-authors that the effect of kerosene lamps, that we can translate the black carbon to CO2 equivalents, because kerosene lights emit CO2 directly, but they also emit black carbon, which is very, very bad for climate change reasons. And so 1 kilogram of black carbon emission is equivalent to 700 kilogram of CO2 emissions. So we translate in what follows all the black carbon into CO2 equivalents. So CO2 equivalents then are the sum of CO2 emission and black carbon emission per lamp used. So it depends on which lamp you use, how much 1 liter of kerosene translates into emissions. And in addition, kerosene lamps emit fine particulate matter, also called PM 2.5, and this is what contributes to these health problems. It can also lead to cancer and severe things. Obviously, in this study, we don't have either the sample size or the duration to pick up these severe things, but we're looking at the milder, shorter term effects. Okay, so going deeper on the emissions, the lower kerosene consumption translates into about 2/3 reduction of both CO2 equivalents, which is the sum of the black carbon and the CO2 from columns 1 and 2, and these microparticles that are bad for health. So it reduces households' monthly emissions by 63 kilogram of CO2 equivalent. So that's really a lot. And I said that in the intro, if all households that use kerosene lighting in Kenya receive the solar light, and under the assumption that they would experience a similar reduction in CO2 consumption, this would lead to a total reduction of 2.2 megatons of CO2 equivalents per year for Kenya. So it's pretty effective. Okay, so now is where we get to how is it worth it for households just for expenditure savings reasons to buy this light. So we have to make some assumptions for that. One is what kind of interest rate we use. So we calculate this both for 7.5 monthly interest rate, which is what people get when they use M-Pesa, the mobile banking in Kenya, or 4%, which is what people usually get in this time and this region if they have a bank account. And so then we find that I think I might have said the wrong numbers in the intro, but so for the basic light, it's between 16 months and 30 months that it would take to pay this off. And for the stronger light, which is more expensive, then it takes about 21 months to pay this off at the cheaper rate. But the stronger light, just from the private returns, never pays off. Never pays off if you don't take into account other aspects from the household's perspective than the lower kerosene expenditures. Here again, we need to make an assumption, which is that the breakage rate is 1.15% per month, which is what we found between the baseline and the follow-up survey. So one could obviously make different assumptions, assume that it starts breaking faster and faster over time, and then these things would become longer.
Dina, you have about 4.5 minutes left.
Okay, great, thank you. So I'm going to go a bit faster here. We're trying to then calculate the cost of averting 1 ton of CO2 equivalents. We did a bit more assumptions here. And if so, then we get to a CO2 equivalent, a ton of CO2 equivalent averted for $7.8 US, which is pretty low in comparison with many other interventions. And so it seems like worth it from an environmental perspective. So now I'm going to show you the outcomes on health and education. So we found actually significant improvements on these shorter term health effects on eye disease and respiratory symptoms, especially for the students. And this is the mixed results on schooling that I mentioned. So we find a significant increase in homework completion and share of homework that's done after dark, also reported hours of homework, even reported hours of school. So I wonder whether because they do the homework, they feel more motivated to actually attend school. Or maybe it has to do also with the health, like if you have eyes that hurt and the cough, you may be less likely to go to school, who knows. But all of that doesn't seem to translate to higher grades. If anything, the point estimates are slightly negative, but not significant, and could be related to they sleep almost a full hour less. Not sure. Yeah. So to conclude, we analyze distributional intervention of solar lights through rural schools in Western Kenya, where most people have neither access to the electric grid in the home nor solar light at baseline. We find that if one thinks about a distribution campaign, that price matters a lot. Even though for the smaller light, this would be profitable just on a basis of future expenditure. It depends also on the personal discount rate of the person. If they might not have the cash or be forward-looking enough to know that it's worth to buy this. So the subsidy makes a big difference. Owning a light then has a very big environmental impact compared to what these households typically consume. It's a 65% reduction in kerosene consumption and emissions. And at the market price, households for the basic light break even at about a year and a half to almost 3 years. So it's a long time for them to break even, but it would be worth it. But again, this is related to maybe subsidies a good idea. Not taking these private benefits into account, the abatement cost of CO2 equivalents is quite low at $7.8 US per ton. So it's probably worth it from a social planning perspective and from an environmental global warming perspective to distribute these lamps, even if there were no benefit to the household. But in addition, we find there's also reduction in health symptoms. So in some, these solar lights reduced expenditures of very poor households, lowered their CO2 related emissions, and improved their health. So it's sort of a win-win for both the environment and poverty reduction. Thank you very much, and I'm looking forward to your comments.
Excellent. Thank you very much, Dina, for a very interesting presentation. Now we have a lot of time left for questions. And please, if you do have any further questions, put them in the Q&A box, and we will then unmute you and call you forward to ask them. And also, we have many people on the panel here, so all the panelists, if you have questions on other presentations, please make sure that you ask them. Starting with the first one, Selina Proffen from Frankfurt has a question for Raul. So, Selina, do you want to ask your question live, please.
Yes, sure. Can you hear me?
Yes.
Perfect. Yes, thank you, all of you, for your great presentations. I just had a question for Raul. And I was wondering whether you had looked at nightlight radiance before and after the start or the initiation of these mini-grid generators. Because you motivated a little bit that you chose this 5-kilometer radius due to the nightlight. And I was just wondering whether you ran any placebo tests before the initiation of these generators.
Yeah, so great. This is a fantastic question. So the problem is that we have data for radiance between 2012 and 2016. The problem is previous data is like the metric they use is kind of different, and actually it's very imprecise, and we see like very strange very strange stuff from, I mean, if we take the data before 2012. Now, if we focus on this window between 2012 and 2016, the problem is that we have very few years. So we have very few like mini grids that were built in this window. See my point?
Mm-hmm.
So yeah, so originally the idea was precisely to use this kind of data, but you know, it's not that easy because either we use the precise data, but then we have a very short window. And then if we use the previous data available before 2012, it's kind of weird. We see kind of very strange patterns, let's say. And apparently it is because this data is not very, like, let's say, trustable.
But with using the VIRS data only, do you see there that there's actually an expansion from before and after about this radiance in the different kilometer sections?
What do you mean?
So if you take these few grids that were connected after 2012. So
yes. So I think I put the figure. So one of the figures in the paper, and I actually show in the presentation, we show before and after for like close, far, and we see an increase. And we see also like a parallel trend in the periods before the installation of the mini grids using just the 2012-2016 window. Okay, so we do this. We have this figure in the paper, and I show in the presentation.
Thank you very much. Yeah, it's good to know because sometimes it's so difficult with rural areas trying even with VIRS data to infer any electrification. So that's good to know that it worked for you. So
yeah.
Thanks, Dina. I also have a question for Raul now while we're at it, and Raul will remember this question because I may have mentioned it before, but maybe you can just reiterate it again. So the example you gave on the geospatial allocation of the mini grids here is like that you're doing distance from the mini grid for different settlements, right? But to what extent is the placement of the initial mini grid already trying to optimize what is the more beneficial close settlement nearby? So in other words, there's two settlements and you're saying, well, what's kind of exogenous here is the distance of the mini grid because you're going to put the mini grid somewhere along the river. But what if they choose the section of the river that is close to the village that they want?
Yeah, so yeah, I remember this question. We need to think carefully about this. So actually we have the slope of all the water bodies nearby. Okay, so we can check that, and for sure we will check. My impression is they are not that sophisticated because these are kind of like small firms, and they just check, okay, so where do we have the better slope? Better slope means the steepest one, because you need, if you don't have the appropriate slope, the water is not going to flow properly in order to like rotate the turbine. So, but definitely we're going to check, you know, to what extent there are like multiple locations for which these hydro mini grids are potentially like appropriate to install. Yeah.
Just quickly to follow up, who's actually who's asking the mini grid provider to come up with a mini grid? Is it the village, and is the village kind of deciding, or is it some external party that's saying this area needs a mini grid and then please find the optimal place for that? from an engineering point of view, because that could give you some further exogenous variation here.
Yeah, so 2/3 of them are installed either by like non-profit organization or like small like providers. My impression for the stuff we've read so far is that these are like motivated because, you know, they have, I don't know, grants from the European Union, grant from the Danish, like a kind of, what is it, like a ministry of whatever, of development, foreign development. And they just, you know, they look for locations and they install them. Different stories, those installed by TANESCO, which is the national company in Tanzania, which is probably like more or less upon request local leaders in these villages. We also can exploit this heterogeneity and see the motives for different like kind of providers, but definitely we need to check into that.
Okay, do we have any further questions for Raul from the other speakers or the audience?
Sure. I guess I have a question that's very related to Niclas's point. In the case of a hydro mini grid, admittedly, you can make a case that the kind of slope and run of the river is essentially fundamental to the efficient siting of the hydro mini grid. But I noticed that concern is perhaps also salient with a variety of the other types of mini grids that are listed in the sample. So for example, for the biomass mini grid, you're essentially assuming that the placement of the road is exogenous. And I think that's a much stronger assumption than the slope of the river. The road itself is optimizing over the placement of the community, or the community is then subsequently being set up in a place where there's access to a road. So I definitely, a lot of the other papers that I've seen that have tried to take advantage of endogenous placement of infrastructure have also attempted to combine, say, wind direction, if it's a coal plant or some other type of approach to really tighten that exogeneity assumption. So I think it'd be worth considering much more closely.
You know, I couldn't agree more with you. So the point here is we're not saying that the location is exogenous. We're saying it's exogenous in a neighborhood of 10 kilometers. Okay, so presumably you're gonna, let's talk about biomass. So biomass is gonna be located where you have like a nearby road, a nearby agricultural facility, because you need to burn the waste, and the location is gonna be given by that. Okay, now if you say this is kind of endogenous or exogenous, it's kind of, I agree with you. This needs to be like further elaborated in the paper. Now, for solar, you need, if you want to install a solar mini grid, you need a lot of space. You need flat terrain. Okay, so you need to find the appropriate flat terrain to build a mini grid. Okay, so probably in a let's say disc of or a circle of 10 kilometers, there are not probably, I don't know if there are many places where you can locate this kind of solar panels, which you need a lot if you want to provide electricity for a few villages. All this is to be discussed, but my impression is that it's not that, kind of tough to believe. But for sure, there is a lot to do.
Okay, any other questions for Raul? Then I think we could just return to our original order and maybe have questions for Faraz. And while people are thinking about it, let me just ask one. We were just talking about sample selection here. So Faraz, I was wondering, in the original RGGVY phase 1 program, right? How did districts select out of that? So the districts not in your sample, did they never submit a plan? Did they not want electrification? Did they only get it later? Were they already electrified? Like, to what extent is your sample selection already kind of giving us a certain type of the population here?
Sure. So RIGV implementation happens in 2 phases, phase 1 and phase 2. Phase 2 happens too late for us to be able to rely on the second round, the 2011 round of the Indian census. And that's primarily one reason why we're exclusively focusing on phase 1. It's my understanding that really the remaining districts at the state level are then selected for phase 2. But the process by which they're going into phase 1 or phase 2 is, we don't observe that, and it's a variety of reasons that might be happening. So we're definitely, that process is endogenous. There's some, political economy reasons why, certain districts might be receiving electrification first. That has implications for the kind of sample that ultimately ends up in our analytical sample. So it is the local average treatment effect of electrification in an RD setup for that sample. And the claim here isn't that the effects that we observe are generalizable to be the effects of electrification in all contexts, but rather the point is that even within that special sample, you see this heterogeneity that's closely related to the complementary economic activity that's happening on the ground. That's a great point. Thanks for raising that.
Thanks. Any other questions for Faraz?
I have one for you, Faraz. So to what extent are your results driven just because, so let me phrase it a different way. So do you expect like long-term impact of this electrification combined with GUR1, considering that probably this fracking boom is kind of like short-term in the US? Because if I'm correct, you're focusing on the time where oil prices were relatively high, so it was profitable to do like fracking. But then in 2016 on, not anymore.
That's a great point. So we do begin to explore that somewhat in our paper by using employment numbers from alternative secondary sources, and in particular, we rely on, if my memory serves me right, about 3 rounds of the economic census of India, which gets us all the way to 2014. And so 2014 is not, given 2005, 2014 is by no means the long term, but it's certainly the longer term. And what we're finding is that those enhanced employment effects for those subset of communities that experience both electrification as well as the economic boom simultaneously seem to persist. Now, it's definitely worth exploring a little bit more why. It could be, for example, that once that initial match is lit for productive uses of electricity through industrial expansion, which we're observing in our kind of shorter term analyses as well, that other businesses emerge that are also able to leverage the presence of that economic activity. If a factory expands and more workers are present, maybe shops also now start opening up to be able to serve those workers. Maybe hotels and residential facilities pop up, which are also taking advantage of electrification so that those workers can live there. This is all conjecture. We don't have any evidence in this, but one could imagine that that's the way in which large-scale infrastructure investments actually begin to provide the kind of benefits that we expect that they will provide.
Okay, any further questions? I have one in the meantime for us, which was basically more clarification, I think, because you're showing these very interesting results on the drop in agriculture employment and an increase in non-agriculture employment. Now, my question was a bit also related to what is the alternative technology that the non-electrified guar producers, what are they using? And to what extent is the boom also making them employ more, and that could be driving? Because I'm not entirely sure how you classify guar workers here. Are they agricultural or are they manufacturing? That's a bit unclear to me.
Sure, no, that's a great point, and we can do more work to be a little bit more precise in our terminology. For our RD results, we're not classifying workers in the guar industry at all. We're simply looking at agricultural and non-agricultural workers. They could be in a variety of sectors, a variety of different types of labor activities. And my sense is that a lot of that shift is happening because just kind of unproductive labor is, the presence of unproductive labor in the agricultural sector is a big problem in the Indian context. When that guar boom happens in conjunction with electrification, what we suspect is happening is that the opportunities available outside of the agriculture sector suddenly become more profitable. If a factory is expanding and it's now hiring more workers for administrative roles, for as security guards and watchmen and sweepers and cleaners, all of these opportunities that previously did not exist are relatively more profitable, relatively more attractive than kind of standing around not really doing much in the agriculture sector. So it need not be that it's technicians and engineers operating a guar processing machine. It can also be the associated jobs that have just arise as a guar processing factory or an establishment begins that expansion process. I'll have to check a little bit more if we have additional data on the precise role of what a worker is doing. I think the point you raised is a really valid one. Is if indeed it's what we're hypothesizing, then we should be able to link it a little bit more directly to specific roles. But at this stage, we're simply using ag and non-ag as kind of crude bins of where labor is active.
And just a quick follow-up, are you then thinking more about the shock here as highlighting potential complementarities of electrification with market access? Or is this more about electrification has heterogeneous effects that do rely on basically making productive use of it? As in like that, the electricity is useless without the opportunity to make use of it. Which of the two is it, if you can ever distinguish them?
Absolutely. And I think this is really the central contribution of the paper to begin to think about that. And I think it's partly in response to some prominent national level evaluations that essentially give us an average treatment effect of about 0 that's imprecisely estimated. And then, the policy conclusion that falls out of some of those papers is that electrification is not the path for development for low and middle income countries. And that's a really bold statement in the presence of very imprecise evidence. And so the main goal of this paper was to show that even when large-scale infrastructure is delivered, complementary conditions on the ground may be central to delivering on the promise of that infrastructure. By no means are we saying that the presence of economic complementarity and rural economic shocks is the only way in which those effects could result in heterogeneous outcomes. It could be that places that have a more educated labor force are better able to take access to electricity and turn that into productive uses. It could be that the presence of other large-scale infrastructure is really essential. So places that have electricity and roads perform better than places that only have electricity or only have roads. I think this is really just a way to open up the broader research agenda and think a little bit more carefully about the heterogeneity that is inherent in real world settings when it comes to large-scale infrastructure. I'm not sure I have an answer of what that precise magic formula is, but that's the kind of question that I think is really exciting for this phase.
I tend to agree for obvious personal reasons. So let's maybe not get carried away here. Instead, let's move over to questions for Dina. Do any of the speakers have questions for Dina? Then please go ahead. If not, in the meantime, I will just ask one, which was, it was a bit unclear to me from the presentation, but that was maybe just me not paying close attention to what extent these PM 2.5 and CO2 measures that then lead to like the back of the envelope later of the impact, to what extent are these measured and how exactly did you measure them? Or are they more estimates derived from usage?
Yes, they are estimates. Exactly, I'm just taking notes here. Yeah, so we have, it's relatively simplified calculation. So again, I would love to have feedback if we should do this better. So we ask what kind of lights the household uses, and we know how much CO2 reduction they have, kerosene reduction they have. And so then we assume that they're using proportionally these lights, and that the reduction comes if they have two lights. If they have one light, it's clear. But if they have two kerosene lights, we assume that they're using half and half. And then we know from other research, 1 kilo of kerosene, how much emission that translates to for this type of a light. And that's how we calculate it.
Okay, and that also means that probably there's like a, at some point you did like a sanity check of like checking if your PM 2.5 reductions and CO2 reductions, if that could actually, if you would go with a meter into the house, if these levels, like the drops in the levels, would actually be realistic, right?
And
Because they
how?
seem
So
quite
what
large,
would
right?
be? That's helpful advice. So what would be a sanity check in this case?
So I guess there must be some kind of technical tools available with which you could actually measure PM 2.5 indoors. I mean, these sensors do exist, and you could just basically go into a house and do go into an average kind of house and do these checks to say, oh, what is the ambient level of PM 2.5 with the kerosene lamp on for 2 hours, and what is it without, and how does the curve of emissions look like over time, etc. To then show, look, we're kind of bringing you from this part of the distribution to down here with the solar lantern. I think Adina wanted to.
Yes, go ahead, Dina.
No, I just wanted to say that was done, but by other researchers, and this is what we base our estimates on.
And how big is that? Are you moving one standard deviation down, or like what's the magnitude?
I think it's reduced by. Let me. Maybe we can see that slide again. I think it's reduced by half or something like that, because we have the baseline, right? So we can see what it's like in the comparison group.
Yeah, but then if both are estimates and not really measured, I think that's what it was.
I see. So you want to just measure, you would like to measure the level in the comparison group and see if that's correct.
I mean, in some sense, get like an actual. If other researchers have done these actual measures, then just highlight that the effect that you are estimating would be basically according to moving in the measured version, moving from here to there along the curve. Does that make sense?
So essentially, we know where it moves in the estimated, and you would want to see whether the estimate that we have for the comparison group corresponds to the actual measured in that comparison group.
I think that's what I'm saying, yes.
Okay.
Raul had another question.
Yeah, I do. So actually a couple of questions here. So first is, I have no clue about the weather in Kenya, but maybe there is a rainy season. So if you have a rainy season, maybe, solar lamps are useless because you need sun. Is this a potential concern? I mean, if you provide or you run the experiment in the rainy season, would you expect to obtain the same results? And the second comment is, do these solar lamps require some kind of maintenance? Because I know like solar panels, you need to clean them like frequently in order, and this is costly and you need to put effort, and some people usually, install solar panels, but they don't put effort to clean them. And then whether this is potentially affecting the long-term results in terms of kind of your results.
So I'm going to say what I know, and then Adina is going to complement with what she knows in addition. So we measure just how many work after 7 months, and it gets us a breakage rate at whatever maintenance they do of about 1.15 of them stop working after a month. So Adina might know more whether that can be reduced to better cleaning and stuff. I think, and here you are all better experts than I am, but I've been told that people tend to underestimate the effect of weather on solar returns, and that even if it's a bit cloudy, that there still could be quite effective. And there's certainly not a season in Kenya where it's not like Sweden, where you might actually have a season without sun. So there certainly is a rainy season, but I don't think there's a dark season. But Dina, why don't you go ahead and jump in with additional background?
Yeah, I mean, not much to add. The models that we chose are extremely simple models. So one of them even has the solar panel. Actually, I have one here. Anyways, has the solar panel like attached to the light itself. So it's extremely simple. The bigger one had it separate, but yeah, I mean, maybe you could get it even to less breakages, but it's a very, very simple device. And we asked and actually measured use as well, like in depth, and it didn't seem that rain or not enough, being able to charge enough or something was a problem.
Faraz had another one?
Sure. I just wanted to say that the focus on CO2 emissions is really exciting. I mean, that's definitely been a big gap when thinking about broader impacts of household level energy technologies. I wanted to, and I'm sorry if I missed this in the actual presentation, I did want to ask a little bit about one key challenge that's been very prominent when thinking about other household level energy technologies, for example, in the cooking space, has been energy stacking, right? So you provide this really efficient new technology and you want them to use that instead of the traditional mud stove, but now they have two and they cook more and they use both at the same time. And so you're essentially exacerbating the emission situation, even by providing an otherwise efficient technology. And I wonder if you observe this in the emissions calculations, if you asked about this in the in your surveys, or if you require them to hand over the kerosene lamp in exchange when you provide these lamps.
Yeah.
Because,
No, great question. So I'll tell you what we do, and you tell us whether we should do something else. But no, nobody's required to hand over anything, and we just ask about how much kerosene the household bought. Period. And so then this is sort of the net effect. They have more light. We see that. So some of it is additional, right? Light. But that doesn't seem to come from like no reduction in the kerosene. Otherwise, their kerosene consumption wouldn't go down that much.
That's a great point. It's probably something to think about for future projects. But in the cooking space, households have actually come out and measured the amount of firewood that they use instead of self-reporting it, and that's helped to provide kind of a fuller picture of exactly what the energy use pattern is.
So your idea would be that because I have solar light, I now cook more?
No. So I'm just kind of providing an analogy for the cooking space.
But so in this case, because the solar the solar has the cost of the whatever CO2 is embedded in the light, and then we know how much kerosene is reduced, so we can sort of weigh these two things together. I think that's the net effect. Dina has her hand up. Dina, you don't need to raise your hand. You can just jump in.
No, yeah, I just wanted to add that also anecdotally. So we can see it because we ask people how much kerosene they use. But yes, this is self-reported. Also, anecdotally, there seems to be a big desire to move away, or this is what people told us over and over, to move away from kerosene. Like, people do not like that product. It smells bad. It's dirty. It creates dirt on the wall. Like, I mean, yeah, you are. I'm sure you're also familiar with these type of responses.
So, if you have any thoughts on like what additional things to measure or to report, obviously we'd be very open to that. As you can tell, I am not, at least as of yet, an environmental economist, so I'm learning a lot through this project.
Okay, we're running out of time, so I just had a very quick final one here, which is we know, and other people have talked about it before, that in the electrification literature here we have this gap in the middle where the macro effects are big, the micro effects are pretty small, but what's actually happening in terms of electrification and development. Now, in this paper with the solar home systems, you're saying that you're moving away and you're saving you're saving emissions, but isn't that just because the solar home systems do not spur any economic activity, which would then increase emissions again? So how do you think about that?
I wouldn't really call it a solar home system. It's really just basic solar light. Okay. And I don't know what the I mean, yeah, it depends what the economic activity would be that somebody would do, but they don't. Yeah, exactly. This is not a light that probably. I mean, I don't know. Have we measured this, Dina? I don't think we have looked at economic activity because of that, right?
I mean, we have time use data.
You have time use data. But yes, I mean, this is a very basic small $9 solar light. That is kind of, yeah, you can charge and then read. So yes, I think that might have very different effects than if somebody then uses that to start and then buys maybe a kerosene driven machine instead, and that goes to Faraz's additional thing. That's I think this is too small for that.
Okay, we have one question from the audience that I'm just seeing now, and we're running out of time, so that will be the last question. Bulime Enoch has a question for Dina. Bulime, do you want to ask it now, please? Bulime, we cannot hear you right now. Okay, don't think we can hear her. So I will just read it out then. Is decreasing emissions by increasing the adoption of cleaner energy sources a priority for the government or households? And what alternative reasons might households have for choosing kerosene or not kerosene? Kerosene or and solar lamps or not solar lamps? I think that was the clarification.
Dina,
I can.
I think I don't know. Instead of taking turns, let's just you start with the better answer, and then.
No, I mean just one point about why would people choose kerosene. It's just how the costs are distributed. It is more expensive over time, but your cost to buy a kerosene light is like 50 cents. And then you pay a lot, but very slowly over time to get the kerosene and to get your light. Versus solar, you have a one-off cost of $9 or more. And then you can use it for free as long as it doesn't break. So, you know, that is for very cash constrained household, a very, very important reason to use kerosene.
And I would assume also just tradition, because as we mentioned in the talk, the price of the lights came down a lot. So this didn't used to be a thing that would have been affordable. And so we know like technology adoption is always something that tends to be quite slow.
Okay, great. Thank you very much. And thanks to everybody for these three very, very interesting and exciting presentations on electrification. Without further ado, let's just close this session and stop the recording. Thank you very much again for everybody.
Thank you very much for the feedback. Really appreciate it.